Hi, this is Bobak. In this video I'm going to solve the following problem for you. Let me read the problem for you first. Find the potential on the rim of a uniformly charged disk, radius r, charge density sigma. This is problem 2.51 from the famous course book Introduction to Electrodynamics by David J. Griffiths, 4th edition, Pearson 2013. There, Griffiths provide us with a hint so that we can solve the problem using the hint. Let me read the hint. First, show that V, the potential, equals to K times sigma r over pi epsilon 0 for some dimensionless number K, which you can express as an integral. Then evaluate K analytically if you can, or by computer. That would be a good idea if you pause the video at this point and try to solve the problem yourself first. If you do it correctly, the answer that you will get at the end is V equals to sigma r over pi epsilon 0. In other words, this number K that Griffiths mentioned to express it as an integral turns out to be 1. Okay, the reason that I brought this problem up because I thought I found a better solution, much easier solution than the way that we want to follow the hint. By changing the perspective of solving the problem from the center to a point on the rim itself. So let me explain what I mean. So assume that this is your disk, so that you want to find and this is uniformly charged with charge density sigma, and then you want to find the potential at a point on the rim. First of all, from the symmetry, you understand that there is no matter on which point I calculate this potential, because all of them have the same potential. So let me choose this point as the point on the rim that I want to calculate the potential at. Okay, so here I will have this center, and let me draw this line. This passes through my center. Okay, and then let me call this point the rightmost point M, and I want to calculate the potential at this point M. Okay, and then what I do, I use symmetry again, because it is clear that if I want to find the potential at this point, the contribution to the potential at point M coming from this upper semicircle is exactly equal to the contribution of the potential at this point coming from the lower one. Yes? So what I do, I will calculate the potential coming only from the upper semicircle and then multiply it by 2. So what I am doing, I am concentrating on calculating the contribution of this charge distribution at this point M. But instead of taking the normal coordinate system, meaning that, okay, addressing any point inside the circle with the standard coordinate, polar coordinates r and theta, I will change my perspective from this point to this point, and I will try to address each point in the upper semicircle by two coordinates again, exactly like the potential, exactly like polar coordinates, but I will show this distance by s to differentiate it with the standard polar coordinate and the angle alpha. Okay, so again you see that my alpha on this upper circle goes from 0 when I am lying on this line up to this point pi over 2, yes? So if I want to address any point, so if I am very close to here, so for example here, this is getting close to pi over 2. If I make s shorter and shorter, then alpha becomes closer to pi over 2. So the range of that alpha is somewhere between 0 pi over 2. It is 0 when I lie exactly on this line. It's pi over 2 when I am on this extreme side. And then this is important to see. Let me start doing the problem, and then we can just discuss about the details. Okay, so let me concentrate on an area element from this perspective. So if I can draw it correctly, so let me, for example, draw this line S, okay, and this is a very narrow angle, so that's an infinitesimal angle actually. So yeah, that's good. So I will concentrate here. I will take this one to be ds. I will call this distance from here to here s, and this ds, and this angle, very small angle there, infinitesimal angle there, I will call it d alpha, and then of course this angle alpha. I will take this as my infinitesimal charge, and I will treat this as a point charge, which is common in these calculations. So I want to calculate the contribution of this charge to the potential at this point. Okay, that infinitesimal contribution dV is equal to, according to the formulas in physics, you know, of course taking infinity as the origin of potential, the zero of the potential, this would be this, and then I have my infinitesimal charge divided, this is the crucial point, divided by the distance of that infinitesimal charge to the point that I am considering. And now you see that this S is that distance. I don't need a more complicated formula to show the distance. Okay? I will show that if you want to follow the hint, that is the hard part. You need to write a fairly complicated formula for S. And this makes the integral calculations harder. Okay, so here I would write this divided by S, but if I continue, remember this is the contribution from the above semicircle. So this becomes 1 over 4 pi epsilon 0. Instead of dq, I can write sigma multiplied by the infinitesimal element of area dA divided by S. But if I ask you what is dA, you can immediately answer it's just like the standard polar coordinates. So this becomes sigma. Instead of dA, I can write the length multiplied by the width, for example. The length is ds, the width is s times d alpha. So this becomes s ds d alpha. Yes, s times d alpha is this length, and ds is that length. If I multiply them, it becomes the area element, infinitesimal area element, and then I have this sigma, so I have written here, and then now you see what is the good point, and now you see what is the good point. The good point is that the denominator is s, and this s and that s are actually cancelled. So what is left for me is sigma over 4 pi epsilon 0, and then I have d alpha ds. Okay, now if I integrate, this becomes sigma over, of course I have a double integral again, but this double integral turns out to be very simple. So I have a double integral, 1 on alpha, 1 on s. Alpha goes from 0 to pi over 2, as I told you. Alpha goes from 0 to pi over 2. But this is crucial to understand that, oh, this is not alpha, this is s. Okay, s goes from where? So assume that I fixed my alpha somewhere between 0 and pi over 2. For example, this alpha. For that particular alpha, you see that s starts from 0 and goes up to this point. Okay, so let me change my color and try to draw that one as well. Okay, so let me take it this. Okay, and then what happens is that for given alpha, my S goes from this point to this point, from 0 up to this length. Now I want to calculate how much is that, yes? So I want to see how much is from here to here. So let me give it a name, for example, K. Okay? So in principle, S goes from 0 up to mk, which is expressed in terms of alpha. But it is very easy to calculate mk. The geometry is very simple. If you connect this point to this point, this angle becomes 90 degrees. Why? Because it is an inscribed angle which is opposite to the diameter, or it subtends a semicircle. So this is definitely 90 degrees. So then it is very clear that what is mk here? Mk is equal to this length, which is 2 times the radius times cosine alpha. So this becomes 2r cosine alpha. So it means that the upper limit is 2r cosine alpha. So I calculate this integral. This will give me the potential of the northern semicircle, yes? And then I multiply it by 2, then I will get the whole potential. But these integrals are super simple to calculate. So let me just do them. So this becomes sigma over 4 pi epsilon 0 integral from 0 to pi over 2 d alpha, and then the integral of ds is just simply s, and it goes from 0 to 2r cosine alpha, so it becomes 2r cosine alpha. So multiplied by 2r cosine alpha. But 2r goes out from the integral, then I will get r sigma divided by 2 pi epsilon 0, and then I have integral from 0 to pi over 2, then I have cosine alpha d alpha, which is very simple to calculate now. You don't need a computer at all. So this becomes sine alpha, and alpha goes from 0 to pi over 2. So this becomes 1. This becomes r sigma divided by 2 pi epsilon 0. But the total potential that is actually wanted in the problem, you need to multiply it by 2. When you multiply this by 2, that 2 in the denominator will be gone, so it becomes r sigma divided by pi epsilon 0. And this is very, very simple to calculate if you just change your perspective from the common origin for the polar coordinates to this point on the rim itself. Okay, so I think in principle the problem is finished here, but I think that's also very instructive if we follow the hint and see what will happen to be able to compare what is the differences between these two perspectives. As you will see, this new method will give rise to a double integral, which is tedious to calculate, and probably you can also feel it the way that hint is stated in the first place. Yes, evaluate k analytically if you can. So that is the challenging set of words for me, or by computer. Okay, I solved that integral, and because it was a tedious integral, I uploaded this solution as another video. If you are interested to see how that integral can be solved analytically, you can refer to that video. You can find the link to that video in the descriptions below this video. But here I just want to start solving this problem from the hint's perspective up to the point that I reach to that double integral. Okay, so let us see why this was easier, but this normal standard polar coordinates, working with normal standard polar coordinates in this problem, gives rise to a more tedious integral. So let me just try to somehow reconstruct the figure. So assume that this time this is again my disk, and I want, as before, to calculate this potential at this point, again I call it M, but this time I want to concentrate on the normal and standard polar coordinates. Namely, assume that I have, for example, a point here. I will consider this as R, and then this is normal theta, but you know that if I want to exaggerate a little bit this infinitesimal element, so I have to draw it like this. So then this becomes theta, and this infinitesimal angle becomes d theta. Okay, again I want to use symmetry as before, so what I do is to calculate so here we don't need to use the symmetry. Okay, so here I can do like this. I can say that the infinitesimal potential is 1 over 4 pi epsilon 0 dq, which is the charge, infinitesimal charge here, divided by the distance of this charge to the point on the rim. Okay, so let me draw this line from here to here, and let me call this one S. Okay, and now I have to divide it by S. But now in this case, this can be written as 1 over 4 pi epsilon 0. Instead of dq, I will write sigma times the area. But the area, this is just a standard polar coordinate, so this is r d theta, and then you have this divided by S. But what you need to do now, you need to express S in terms of your polar coordinates r and theta, which we didn't have to do in the previous way of solving the problem. And then this is also simple, not hard to write this. Solving the integral would be a little bit harder, because from here to here is r, so let me mention it here. This is r, and then if I use the cosine rule, I know that s squared in this triangle, s squared is r squared plus capital R squared minus 2 times little r times capital R multiplied by the cosine of the angle between these two sides, which is actually theta. Okay, so it means that dv is equal to 1 over 4 pi epsilon 0. I can put sigma here. Then I have r d theta, then divided by, I will take a square root to find s itself, so it becomes r squared plus r squared minus 2r cosine theta. And if I want to continue and find v, here of course you can use symmetry. To solve that integral at the end I will use symmetry, but let me just write it like this. So this becomes sigma 4 pi epsilon 0, and then that's a double integral. So this double integral r d theta divided by square root of r squared plus r squared minus 2r cosine theta on disk D. So if you want to write it mathematically, so disk D, it contains all the points x and y in r squared, such that x squared plus y squared is less than or equal to r squared. So the point, if I want to calculate this integral, if I want to calculate this potential, I have to calculate this integral. And that is the tedious integral that Griffith challenges us to calculate it if we can otherwise use the computer to solve it. So you can find the link below this video for the solution to this problem. I was able to show that this integral, where D is this domain, is equal to 4R. Okay, and then if I have this equal to 4R, I multiply 4R here. Yes, so I will have 4R here, and then 4 and 4R cancel. Then I will have R sigma divided by epsilon 0, which is exactly this one. So showing that this double integral is equal to 4r is the subject of the video that you can find the link below this video. I hope that you found the video somehow useful for you. Until the next video, be safe and goodbye.